We have so far introduced the three main components of machine learning. Data in the form of data points characterized by features and labels. A model is then used to learn a useful hypothesis map that allows predicting a data point's label from its features. Besides data and model, the third main component is a loss function. A loss function measures the quality of a hypothesis. Formally, a loss function assigns a number to a pair that consists of a data point and a hypothesis. Different machine learning methods use different choices for the data representation, model, and loss function. In what follows, I will detail the design choices underlying some widely used machine learning methods. The important family of linear machine learning methods shares a common choice for the model, that is, the set of linear maps. However, we obtain different linear methods by using different loss functions. For example, linear regression uses squared error loss. In contrast, logistic regression uses the logistic loss. Note also that linear and logistic regression differ in the data representation. Indeed, linear regression can only be used for data points with a numeric label value. In contrast, logistic regression is a binary classification method for data points whose labels indicate their belonging to one out of two categories. Deep learning methods represent a hypothesis space using artificial neural networks with many layers. Note that deep learning methods differ in their choice for loss functions and data representations. In particular, there are different deep learning methods for audio, video or image, and text data. Three main flavors of machine learning are supervised, unsupervised, and reinforcement learning. These three flavors correspond to specific types of loss functions. Examples of supervised learning methods include linear and logistic regression. Unsupervised methods include principal component analysis and k-means clustering. Examples of reinforcement learning methods include contextual bandit methods and deep reinforcement learning. Supervised machine learning methods use loss functions that explicitly involve the actual label value of a data point. Examples of such loss functions are squared and absolute error loss. Also, the evaluation of the logistic loss, the hinge loss, and the 0-1 loss require the label value of a data point. Supervised learning often requires a sufficiently large number of data points whose label values are known or have been determined. Note that the labeling of data points might require significant economic resources. Therefore, we typically prefer machine learning methods that require a minimum amount of data points with known labels. Unsupervised learning methods use loss functions that do not require the actual label value of any data point. A prime example of unsupervised learning is the clustering method k-means. Here, each data point is characterized by several numerical features and by its cluster assignment. We can interpret the cluster assignment of a data point as its label, which identifies the cluster to which the data point belongs. K-means uses a loss function that is determined from the spread of the data points around its cluster mean. However, the loss function of k-means does not require the actual label or cluster assignment of any data point. unsupervised methods are appealing as they do not require data labeling. Reinforcement learning is maybe the most advanced form of machine learning. These methods do not compute the loss directly from the predicted and the true label. Instead, reinforcement learning constructs a loss function from external signals of the physical environment. For example, consider a machine learning method that predicts the optimal steering direction for a car. We can interpret each time instant during the car ride as a data point. The features of such a data point are the snapshot pixels of an onboard camera. The quality of the used hypothesis, which delivers the prediction for the steering angle, can only be measured indirectly, for example via distance sensors that indicate if the car stays on track. A key challenge in reinforcement learning is that for each data point, the loss function can only be evaluated for one single hypothesis. Indeed, the self-driving car can only try out one prediction for the optimal steering angle in any given time point. It simply cannot explore two different predictions for the steering angle at the same time.